Hello. Today we are going to review experiment 6, the flame test thing, talk a little bit about it. We'll talk a little bit about the exam, and then we will do chapter 5, chemical reactions. This is an emission line spectrum for a fluorescent light. We'll see it again in a minute. If you use a spectroscope, you can break the white light from a fluorescent tube down into something like this. What we did was a flame test. Now I said the classic way to do a flame test looks something like this. Have a glass rod with a little platinum wire embedded in it. You dip the end of the wire into a solution. You stick it into a flame and you see a color. Now the color you see is actually an average. Your eye is averaging all of the lines in the emission spectrum. Problem with doing this is you really need a platinum wire in order to make this work. They won't give us platinum wires anymore. So we use nichrome, and nichrome always burns yellow, just always does. So instead of that, we did it the fun way, using the blowtorch method here, where we take a pressurized can with our stuff, blow it into a flame, and see the color. Now I tried to explain without visual aids where these colors and lines come from. Basically, this is our quantum description of an atom. We have electrons living in shells. They are quantized. They correspond with a period. When this particular atom absorbs energy, these electrons can be promoted from where they used to be to somewhere else. Now, they look at each other and perhaps say the view is good from up here, but I want to go home. Unfortunately, they have absorbed this energy, and the process of going home means they have to lose that energy. As they do, they emit a quantized photon of light. It will have a single wavelength corresponding to the stair step that is coming down. So there's one, there's another, and if you look at the emission spectrum, these show up as distinct lines. Once again, your eye averages these. We can break the average apart using a spectroscope, shine this at fluorescent lights, and again, this is what we see. Very bright, nice lines corresponding to the fluorescent material that's inside the tubes. Now, doing the blowtorch method is so much more fun than simply dipping a wire in the solution. It really is. But the absolute best way to do this is, well, works best if you're in a lecture hall where you can shut off all the lights so the room is totally dark. And what you're going to do is basically set your desk on fire. You have little watch glasses with the salts in it on your desk, and you pour alcohol, flaming alcohol over it, and you get the flame test. Let's watch the fun one. Dark room, there you go.
Very dramatic version of the flame test demonstration here. First we have alcohol burning blue, then we have some barium chloride with barium ions burning a yellow, a dirty yellow color. Then we have boron being green, strontium giving us the crimson red color. Next is calcium giving us the orange. Not showing up very well here in the next one, but the red tints inside of that orange there's some impurities there. That is lithium. Next we have sodium giving us a characteristic yellow flame. Then we have copper with its green color, and finally potassium with the purple or lilac shade.
Now this is yet another demonstration they won't let me do here, but believe me, I've done it. It's really fun. Any questions? Where do the colors in fireworks come from? Well, here's a classic firework display, perhaps the best I've ever seen. And the colors go everywhere from blue down to pink. Cobalt, sodium, copper, strontium, iron, zinc, lithium. Put the metal salts in with the gunpowder. When it burns, you get the color emission. The whites in the middle are probably magnesium. Very bright white light. Any questions? All right, exam one. High score was 103. It was amazing. What you should do is go to Blackboard, check your total score. Depending upon the mood that Blackboard is in, it may show you different things. You want the one that simply says total, not running total, not weighted total, total. If you're 175 or over, you're doing really well. You're on your way to acing this course. There is one question that I wanted to talk about, because about half the class, maybe 2/3 of the class, missed it. Compound C3H4 with one carbon-carbon triple bond, draw the Lewis structure. Well, okay. We have carbon and hydrogen, group 1, group 4. Every carbon will have 4 valence electrons, every hydrogen 1. So we're dealing with this. 3 carbons, 4 hydrogens. Now if you read the problem, we have one carbon-carbon triple bond here, don't we? So let's take and move some electrons in. Here we made a double bond, move those up, and we make a triple bond. Now finally, takes 2 electrons to make a bond, right? We have 1, 2, 3, 4 unpaired electrons and 4 hydrogens with 1 each. Simply place them around. Our carbon here in the middle has 8 electrons. So does this guy, and so does this guy. Every hydrogen has 2, and that's all they can hold because of the first period. This is the organic compound, propyne. Now I said before class, and on the exam in writing, that you might find it's easier to do if you use the rules. So let's look at it by the rules. Step 1, count the valence electrons and hydrogens. Once again, group 1, group 4. We have 3 carbons, 4 hydrogens, that's 16 electrons. Rule number 2, attach atoms to the central atom and give them all an octet. Well, okay, we have 3 carbons, one has to be in the middle, right? And these guys each have 8 electrons now. Place any remaining electrons? Nope, we're out. You've used all 16. Make double or triple bonds if necessary. Well, we know it has 1 triple bond. So, move them in. There's our triple bond. Finally, add the hydrogens. We're going to go 1, 2, 3, 4. And there's our propyne. Seems so simple when I do it, doesn't it? Any questions? All right, let's go ahead and do chemical reactions. This is yet another demonstration they won't let me do. It's the um, reaction between aluminum and iron oxide. It's very violent, very fun, wonderful thing to do. We'll talk about this a little bit later. Before we get started though, there's a mistake in the syllabus because they changed the date of lab makeup. Now, lab makeup doesn't really apply this semester at all. It's a snow day where everybody's stuck at home, right? Well, we didn't have snow, did we? So, just a day off. What they did is they moved it into the Wednesday before spring break to give you a little bit longer break if you wanted. So, no class on Wednesday, have a nice break. Chapter 5, chemical reactions. We've seen this slide many times. Aluminum plus bromine makes aluminum bromide. This is the chemical change. These combine in a specific and constant ratio to make a compound. We show this using a reaction arrow that links reactants and products. Now the reaction arrow, we said, was like an equal sign. Basically, it tells us when we have the arrow here, we must have the same number and types of atoms on both sides of the equation. If we look at our equation here, we have 2 aluminums here, 2 aluminums here. We have 3 times 2, 6 bromines, 2 times 3, 6 bromines. So yeah, it works. The little letters down here correspond to the physical state. Now they're optional, but quite often they're useful. S is for solid, liquid, again solid. G is gas, HU is aqueous solution. That means it's dissolved in water. Now, the requirement here from our arrow, our equal sign, is that we must have the same numbers and types of atoms, right? If we take and we express that in terms of molar quantities, we can take this equation and simply say we have 2 moles of aluminum reacting with 3 moles of bromine to give us 2 moles of aluminum bromide. This is referred to as the stoichiometry of the reaction. Now, stoichiometry is a wonderful word. You can tell people, yeah, we talked about stoichiometry today. Sounds really impressive. All it is the coefficients in your equation. When we describe this in terms of moles, remember, moles can also be represented by a molar mass. So we could say, this shows us 53.96 grams of aluminum reacting with 479 grams of bromine, give us 533 grams of aluminum bromide. That's the mass stoichiometry of the reaction. We will do that in chapter 6. Also, note conservation of mass applies. Add this and this together, you always get this. Any questions? Well, the real question should be, yeah, they're the same number and types of atoms, but to do that, we had to stick in these coefficients, didn't we? Where do they come from? Well, you kind of take an unbalanced equation and you mess with it until you get it right. Consider hydrogen peroxide, aqueous solution will decompose to give oxygen gas and water. Now, if we look at this equation, right away we can tell it's not balanced. We have two hydrogens and two hydrogens, that's good. But we have two oxygens here, and we have 1, 2, 3 on this side. Now, there are many strategies that people use to balance equations. I tend to try to make both sides of the equation either even or odd. In this case, we have two oxygens on this side, and we have three oxygens on this side. That's an odd number. We can never get the coefficients to work unless they're both either even or odd. To make this even, we could simply put a 2 in front of the water as our coefficient. That now gives us two oxygens. We have 2 over here. At least they're even. They're not the same, but they're even. Now we can fiddle with it more. We have 4 hydrogens here now because we put a 2 in front of our water. Only 2 on this side, but we can fix that by sticking a 2 out here. So this gives us 4 hydrogens, 4 hydrogens. 4 oxygens, 1, 2, 3, 4 oxygens. 4 hydrogens, 4 oxygens. We have balanced this equation. The way to learn to balance equations is by balancing equations. Doing this over and over, we'll do a bunch of examples in a bit. Any questions? Well, at the end of chapter 12, looking far ahead, we have exam number 2 coming. After that comes the final. We just had exam number 1. This is a question off the final from a couple years ago. What I wanted people to do was to take this sentence here, convert it into an equation, and then balance it. Well, we've done nomenclature. We're doing balancing now. We can do this, right? We have potassium chlorate. We remember the chlorate, the parent of the chlorine family, ClO3 minus 1 charge. Potassium, group 1 metal, plus 1 charge. That's it. Decomposes to give oxygen gas. Now remember, oxygen is diatomic. It exists as O2. If I wanted oxygen atoms, I would say so. Oxygen gas is simply O2. And finally, potassium chloride, group 7, group 1, that's KCl. All right, here's our basic equation. Is it balanced? We have 3 oxygens, we have 2, so no, it's not. I would balance this by first looking and saying, okay, if I put a 2 out here, double the KClO3, that'll give me an even number of oxygens to work with. So there's our 2. Now, this gives us 6 oxygens, right? We have 2 on this side. We can get 6 on this side if we stick in a 3. This gave us 2 potassiums, 2 chlorides. We only have 1 of each here. We need another 2. And we have balanced our equation. Any questions? Well, this particular reaction is a useful sort of reaction in lab. Sometimes you're doing things on a very small scale where you need a bit of oxygen. You can take potassium chlorate, heat it up, and you get oxygen gas. Nice, pure, clean oxygen gas. This is a gummy bear. Okay. We are going to take our gummy bear. We are going to take some potassium chlorate, heat it up, so we start making oxygen. Now the gummy bear is almost pure sugar. That sugar, it will react very, very rapidly with the oxygen that's being produced under the hot conditions and will react to give CO2 and water. So this is called the gummy bear reaction. It's a video clip you should not share with young children. We have heated up our potassium chlorate. See the oxygen bubbling?
Ouch!
And there goes our gummy bear. And it's over with. Poor guy. Sugar, oxygen, CO2, and water. Any questions? Well, let's get right to it then. And let's balance some equations. So, let me see if I can get this thing to work. All right, we look at our first one. I see we have 2 hydrogens here, 3 hydrogens here, right? Odd even. I can make both sides even if I double the amount of ammonia that's produced. Now, this doubling gives us 2 nitrogens. That's good because that's what we have, right? It also gives us 6 hydrogens. We only have 2 on this side. We need a 3. 3 hydrogens, 1 nitrogen into 2 ammonias. And I got it right. Look, when that happens, you know. Zinc reacts with HCl to give zinc chloride and hydrogen gas. We have 1 zinc on each side, that's good. But we have 2 hydrogens and 2 chlorines here and only 1 on this side. Fix that. We can simply stick a 2 in. Yep. All right, this next one's a little more complicated. Take a minute and see if you can get this. Step 1. We have 3 oxygens. We have 2. So we're going to double this guy. Now, when we do that, that gives us 4 irons. And we have 1 on this side. let's fix that. It also gives us 6 oxygens. Only have 2 on this side. We need a 3. And now how many chlorines do we need? Well, chlorine exists as Cl2. We have 4 times 3, 12 chlorines. We need a 6. Yep. Any questions? All right. Do these. One sodium on each side, 1 oxygen on each side. We have 2 hydrogens here, 1, 2, 3 on this side. So let's fix that by putting a 2 in here. Now we have 1, 2, 3, 4 hydrogens. Only 2 on that side, but at least it's an even number. By doing this, we gave ourselves 2 sodium, so we need to fix that. And let's see. We have 1, 2, 3, 4 hydrogens. Here we only have 2. I think that ought to work. Yep. The next one. One hydrogen, 2 hydrogens. 1 chlorine, 2 chlorines. Pretty straightforward, I think. If we double the amount of HCl, we now have 1 lead, 2 hydrogens, 2 chlorines on each side. Now, when we look at a reaction involving polyatomic ions, you want to remember the polyatomic ions are basically always treated as little lumps. They're just basketballs, okay? They got a bunch of atoms in it, doesn't matter. Treat it like a basketball. On this one, we have 1 silver, 1 nitrate. 1 silver with 2 nitrates. We're going to have to fix the nitrate problem, aren't we? Now, that gives us 2 silvers, only 1 on this side. Hmm? Yeah. So 2 silvers, 2 silvers, 2 nitrates, 2 nitrates, 1 magnesium, 2 chlorines. Yep. Any questions? Now there's a tutorial. Tutorial is on Blackboard as well. This is the one on Chemistry Online. Balancing chemical reactions. We are given a reaction. Now, I'll be honest, this pulls from a set of equations, and some of them are a little bizarre, a little advanced. If you get an equation that looks like whatever to you, click New Problem and try again. Okay? This is nice and simple. We look here, we have 1, 2 carbons, only have 1 on this side. We would have to put a 2 in here. We have 1, 2, 3, 4 hydrogens, only 2 on this side, double that. Now we have 1, 2, 3, 4 oxygens here, and 2 more here, that's 6. This has to be a 3. Any questions? The one thing you have to remember on Blackboard, remember you can't leave a field empty. So when you do this on Blackboard, you have to put a 1 in, even though that is not typically done. Got it? There's another one. This is calcium carbide. Calcium carbide is an interesting solid. It reacts with water to form acetylene gas and calcium hydroxide, which is insoluble in water. Well, acetylene, you may know, burns. It's an organic gas. Use it in welding torches, things like that. So it's a very useful reaction. 1 calcium, 1 calcium, we're fine. 2 hydrogens, 1, 2, 3, 4 hydrogens, that's not fine. Oh, the acetylene here. Know what this is? That's an old-fashioned miner's helmet. A little button here with some calcium carbide. You push the button, it drops into some water, and you light the top of your head. Go down deep in the mine, you can see. You hope, of course, that the mine is not filled with methane gas and that explodes. But they don't do this anymore, but they did that for years and years and years. All right, we need a couple waters. That's 4 hydrogens, 1, 2, 3, 4 hydrogens, 1 calcium, 2 oxygens, 1, 2 oxygens. Yep, we're set. Now, calcium carbide also brings back memories for people from my generation. This is what was called a Banksite cannon. I don't think you can buy them anymore. But in this little thing up here, you would put calcium carbide. In the bottom of the barrel here, you would put water. This is a striker that would make a spark. So you would take your cannon, you would fill it with water, fill it with carbide, push your button, and it was great fun. You could stuff stuff down the barrel, it would shoot it halfway across the yard. It was fun. This is how a whole generation of chemists grew up. There is a sheet on Blackboard called Balancing Equation Worksheet. No credit for this one, but there are just lots and lots of problems here. They're all of the same sort of difficulty that you would see on an exam. So a very nice way to practice. There's also an answer sheet. Any questions? All right, let's look at types of chemical reactions. The reason that we're going to try to classify reactions by type is if you know the type of reaction, it makes it basically easier to predict the products. So let's look at our basic types. Synthesis and decomposition. Synthesis, we're taking two or more substances and making something new. Decomposition, just the opposite. We're taking one and we're making a bunch of new stuff. Example, carbon plus oxygen gives CO2. Think charcoal, okay? We are taking elements, we are reacting them and making a compound. Well, synthesis from the elements. We can also do synthesis from compounds. Here we have the organic compound ethene reacting with hydrogen bromide to give bromoethane. All compounds, we can do synthesis from both. Decomposition is just synthesis backwards. Copper 1 sulfide, if you heat it up, will form copper metal and sulfur. Sulfur burns off. This is a very old way of making copper. Decomposition into the elements. We could also decompose into compounds if you take calcium carbonate. Calcium carbonate is marble, okay? It's chalk. It's concrete. We can heat it up, make calcium oxide and CO2. The reaction going back, if you take marble and you cook it, you get calcium oxide. If you then add calcium oxide to water, it will absorb CO2 from the atmosphere and give cement. It's a cement reaction. We did a decomposition in lab. Ammonium hydrogen carbonate. Put it in a tube, we heated it up. We did not stick it up our nose. We got ammonia, a very pungent gas, CO2, and water vapor. Any questions? Replacement reactions, they come in two forms, single replacement and double replacement. In a replacement, two compounds or an element in the compound react so that the atoms are switched. All right, that doesn't make much sense. Let's look at an example. Here we have an element and a compound. We are going to react those, and we will make an element and a compound. However, note the fluorine has replaced the chlorine. They're switched. There's a general rule for single replacement reactions. Metals will replace metals, so something could replace the lead. Nonmetals replace nonmetals. The nonmetal fluorine replace the nonmetal chlorine. The signature of a double replacement reaction. Element and a compound, give an element and a compound. We did this in lab as well. Remember, we took a nice nail. The element, our compound here was copper 2 nitrate. We deposited the copper on the nail and we're left with iron nitrate in solution. This is called a double replacement reaction. In a double replacement reaction, we are taking ionic compounds, typically in solution. We are allowing them to react. We will form a solid insoluble substance and another ion that stays in solution. So 2 ions, an ion, and a solid substance. This is called a precipitate. What we do basically is we swap ions. Oops, let's go back to that one, sorry. The sodium has replaced the silver bonded with the nitrate, and the silver has replaced sodium bonding with the chloride. In order for a double replacement reaction to occur, something must be insoluble in water. We'll talk about water solubility in a bit. Redox reactions, oxidation and reductions. One or more atoms undergo a change in oxidation state. Let's look at our carbon plus oxygen to give CO2. Now, back when we were doing chapter 3-ish, we very quickly looked at oxidation numbers, right? I said there were a couple things you had to remember. Elements are always 0, and oxygen were always going to be -2. So, we're starting off with 2 elements here. Their oxidation numbers are 0. Over here, our oxygen is going to be -2. To make this neutral, we have 4 negatives. The carbon must be +4. So, have oxidation numbers change? Absolutely. 0 to +4, 0 to -2. This is a redox reaction. Again, we'll talk more about those in a minute. Let's do some simple stuff first. What are these guys? Synthesis, decomp, or replacement reactions. Well, we are taking 2 elements here, and we're making a compound. That's an example of synthesis. Synthesis specifically from the elements. Here we have an element and a compound. We're making an element and a compound. That's the signature of a single replacement reaction. The nonmetal has replaced the nonmetal. Aqueous solution of sodium sulfate and barium chloride. We mix these together, we get insoluble barium sulfate and sodium chloride, which stays in solution. This again is a signature double replacement reaction. Any questions? Hydrogen peroxide, you warm it up, you get oxygen gas and water. You're taking one substance, one compound, and you're making 2 or more different substances. We are decomposing the hydrogen peroxide. How about the next one? This was actually an exam question. Everybody looked at this and wanted to say it was a single replacement reaction because we have an element and a compound, right? But what are we making? The compound. Where's the element? There is none. It's simply synthesis. And finally, we balanced this earlier. This one does have an element and a compound, making an element and a compound. The nonmetal replaces the nonmetal oxygen, give us iron chloride and oxygen gas. Single replacement. All right, let's predict a couple things then. Synthesis reaction involving metals. It's important if you see you have what looks like a synthesis reaction and you're trying to figure out the products, to first look and see, is there a metal involved? If there's a metal involved, our product is going to be ionic. So we need to remember that. We've seen this reaction before. It's fun to look at. Aluminum goes into bromine. Huge amount of toxic fumes are emitted. Now, I've never done this one in class. One of the few I haven't done. Huge amounts of toxic gas. And we're left with our solid white residue. All right, so we have a metal involved. It's going to be ionic. What you want to do is look at the typical charges. Aluminum will be a +3 ion because it's group 3. Bromine's a halogen. It will be a -1. Our best guess for the product, 1 aluminum, 3 bromines. But is it balanced? Of course not. Quickly balance the equation. One aluminum, 1 aluminum. No problem. 2 bromines, 3 bromines. We're going to have to make this even. Take a 2 in. Now, to do that, we need 2 aluminiums on this side. We have introduced 6 bromines. They come as pairs, so we need a 3. That's our equation. Any questions? All right. If you're doing a synthesis or decomp and we have nonmetals, what do? This is where you go back to the good old-fashioned Lewis structure. We're going to take hydrogen, react it with oxygen. It's kind of an interesting reaction. It's loud. Fun to do. And we're going to make something. What you want to do here is to look at the number of valence electrons you're dealing with, because it's going to be a molecular compound. So hydrogen will have 1. We have 2 of them. Oxygen will have 6 electrons. Very clearly, these line up nicely to make water. Now, are we balanced? Of course not. 2 oxygens, 1 oxygen. What are we going to do? Simply double it. Now we're even. We have 4 hydrogens here, only 2 on this side. Kind of double that. 2 oxygens, 2 oxygens. I think we're good. Now that's synthesis. One more time. For a synthesis, you look to see if you have a metal. That will tell you if you're making an ionic compound or a molecular compound. For a decomposition reaction, however, there's no clue what's going on whatsoever. You simply do it and you try to figure it out based on what you see. This is nitrogen triiodide. It's a very interesting compound. It's a contact explosive, perhaps the most sensitive contact explosive that exists. These are little filter paper discs. What you do to make this, quite simply, is to take ammonia and iodine in water, mix them together. This black stuff falls out of solution. You kind of swirl it around, run it through filter paper. As long as it's wet, you're okay. This has been allowed to dry out. Watch this. Here comes a feather. Literally. Even in slow motion, it's even amazing. That was from touching it with a feather. All right, so what's our products here? Like I say, with a decomposition, you never really know. You just have to look at the clues that you have around. The one clue here is this giant purple cloud. And that's because iodine, by George, is purple. It has a high vapor pressure, so there's always a cloud of iodine coming off of it. Our best guess here is that we're making molecular I2. We're decomposing into elements. So the nitrogen will wind up as N2, iodine as I2. Many explosives, most explosives, involve the production of nitrogen gas. Very stable, has that triple bond in it. All right, we're not balanced. Quickly balance. One nitrogen, 2 nitrogens, 3 iodines, 2 iodines. Let's stick a 2 in front and solve 2 problems at once. We now have 2 nitrogens, so we're good. And we have 6 iodines, even number. We need a 3 here. Any questions? All right, single replacement. Here we're going to take a compound and an element. We're going to make a compound and an element. We remember metals will replace metals, non-metals replace non-metals. Example, here we have lead 4 chloride reacting with fluorine gas. The non-metal will replace the non-metal. Lead will stay +4. And this is our products. Compound and an element, compound and an element. Now, of course, it isn't balanced, so quickly do it. Now, in this one, we don't have an odd-even issue, do we? Everything is either odd or even on both sides, but the numbers are so wrong. We have 2 fluorines here, 4 here. We gotta fix that. We have 4 chlorines here, 2 on this side. Gotta fix that. 1 lead, 1 lead. Any question? All right. Metal replaced metal, non-metal replaced non-metal. Nice thing to remember. It works 98% of the time. The couple of times it doesn't work are perhaps the most important single replacement reactions in industry. For example, if you take copper 1 oxide, heat it up in the presence of hydrogen gas, you get metallic copper and water. This is a nonmetal, so is the oxygen. You would expect the hydrogen to replace the nonmetal. Instead, hydrogen is acting as if it's a metal, and it's replacing the metal. This guy, iron 3 oxide plus carbon, gives iron. Once again, carbon is acting as if it's a metal, replacing the iron to give us metallic iron. This obviously is a nice simple way to make copper solid without dealing with the sulfur. This, hello, is what they do in Gary. Take iron 3 oxide, take carbon, that's coal, heat it up in a giant blast furnace, and make molten iron. Perhaps the most important 2 single replacement reactions are exceptions to the rule. If you notice on the periodic table that came with the exam, hydrogen was listed twice, once as a metal, once as a non-metal. That's why, because here it is pretending to be a metal. Any questions? All right, double replacements. Very simple rule. Cations replace cations, anions replace anions. Something must happen. We must get an insoluble product or a gas or something like that. If we take potassium sulfate and barium nitrate, both in aqueous solution, mix them together, we will get an aqueous solution of potassium nitrate and barium sulfate solid. The barium swaps out, pairs with sulfate. The potassium swaps out and pairs with the nitrate. Now this precipitate, like I said, all of these reactions, at least the ones we're doing yet right now, are going to have a solid form. Okay? Here's an example. If we take potassium iodide and lead to nitrate, they're both clear, colorless liquids. if we mix these together, we will get lead 2 iodide as a solid and potassium nitrate staying in solution. The reaction is pleasant to watch. It looks like this. Again, clear solutions. The second they touch, we form the insoluble lead 2 iodide. If you let this sit long enough, it will settle down to a little plug in the bottom of the tube. Very insoluble. All right, how did I know that lead 2 iodide was going to be insoluble? Because I happen to know the rules. Now, there are rules. Nobody likes rules. But they're not really that complicated. On exam number 2, again, you can bring a 3x5 card. If you want to waste it on rules like this, that's fine. But anything that you need. First of all, look to see if we're in group 1 or if it's ammonium cation. If it's either of these guys, it will be soluble, regardless what it's paired with. Group 1, soluble. If it's a nitrate or an acetate, acetates will be big for you in general chemistry. Nitrates are big now. They're virtually all soluble. If it's a nitrate or an acetate, it's soluble. If it's a metal halide, now the halogens are group 7. A metal halide is going to be soluble. Think sodium chloride. Except for our group of heavy metals. Our heavy metals in chemistry are silver, lead, mercury, and copper. If either of these is a cation, it is not soluble. Same thing with sulfates. Sulfates are going to be soluble unless it's a different group of metals, barium, lead, and calcium. Those are insoluble. Finally, hydroxides and oxides are going to be insoluble unless Rule 1 wins out. Same sort of thing for carbonates, phosphates, hydrogen phosphates, all of the other ones that you don't remember. They're insoluble unless Rule 1 applies. Now, like I said, nobody likes rules, but they're easy to apply. Let's do it. Here we have silver nitrate. We remember silver as being a bad guy, right? But it's paired with nitrate. What do we know about nitrates and acetates? They're all soluble. Okay. Magnesium chloride, that's a metal halide. We know that there are exceptions for metal halides, like silver, for example, lead. But magnesium, nope, not a heavy metal, is it? It's soluble. Silver, lead, mercury, and copper are not. Most sulfates are soluble, aren't they? Not only that, sodium, group 1. it's going to be soluble anyway. Sulfates, the bad guys, are barium, lead, and calcium. There's our friend silver again. We know that it's a bad actor sometimes. It's a bad actor when it's combined with a halide. Silver, chloride, heavy metal, insoluble. Most of them are soluble. Silver, lead, mercury, and copper are not. Barium nitrate. Well, barium's a group 2 metal, right there. But it's a nitrate. All nitrates and acetates are soluble. Lead iodide, we just saw that in the movie, starring in the movie. Beautiful yellow substance. Most metal halides are soluble except for the heavy metals. Lead, silver, mercury, and copper. Magnesium nitrate. Hey, it's a nitrate. It's soluble. Most sulfates are soluble, except for 3. This is a big one. Make sure you remember this one, lead iodide. They're key things to remember. Barium sulfate is insoluble. Barium, lead, and calcium, solids. Iron 3 chloride. Most metal halides are soluble. This is iron. We could call that a heavy metal, but it's really not. Heavy metals are reserved for lead, silver, mercury, and copper. It's soluble. And finally, what is this thing? Again, general chemistry, you will learn to love it. That's acetate. Lead, acetate. Lead's a bad actor, but all acetates and nitrates are soluble. Any questions? Well, let's put all this good knowledge to use. These are double replacement reactions. What I'd like you to do is decide what the insoluble stuff is going to be. Write the ionic compound that stays in solution, and then balance the equation. I'll pause for a minute while you get started. First of all, let's look at here. Our anions are nitrate and carbonate. All nitrates will be soluble. That's why silver nitrate is soluble. Carbonate. Most carbonates are not soluble, virtually all. Why is this soluble? Because it's group 1. So, silver carbonate is going to be our solid. Potassium nitrate is left in solution. Now, we look at this and we say, gee, not quite balanced, is it? We have one silver, we have two silvers. We have to fix that. That gives us two nitrates, so we do that. Only one on this side. Fix that. So, two silvers, two silvers. Two nitrates, two nitrates. Two potassium, one carbonate, and we're good. Look at the next one. Carbonate will pair with the copper and give us insoluble copper 2 carbonate. Potassium will pair with nitrate. And that's what we get. Once again, we're not quite balanced. One copper, one copper. One carbonate, one carbonate. Two nitrates, one nitrate. Two potassiums, one potassium. All we need is our 2. Again, carbonate's the anion, aluminum carbonate is going to be our solid. We will wind up again with potassium nitrate. Quickly balance it, simple to do. We have one aluminum, we have 2. Let's double it. We have 3 nitrates. We have 1 here. We have a 2 in front, total of 6 nitrates. This gives us 6 potassium. We only have 2, we need a 3 here. So we have 3 carbonates, 3 carbonates. 2 aluminums, 6 potassium, 6 nitrate. I think we're balanced. Let's mix it up a little bit. And these are designed for you guys to do without me. So again, I'll sit down for a minute. In our first one, magnesium will pair with the nitrate. Silver will pair with the chloride. It will be insoluble. So silver chloride is our solid precipitate. We have 2 chlorides, we're going to need 2 silvers. Nitrate is -1, magnesium is +2. So we're going to need 2 silver nitrates for every one of these guys. I think that works.
What is the S again? S. What is the S?
Yes, solid. Follows out of solution as a solid. Barium here will pair with sulfate. We know that most sulfates are soluble except for barium. Sodium sulfate is our remaining ion in solution. Barium is a +2, sulfate's a -2, that's good. Nitrate's -1, sodium is +1, and we have 2 of these guys. So we simply need a coefficient of 2 in front of our sodium nitrate. Our last one here. We didn't talk specifically about sulfide. Sulfur is right underneath oxygen in the periodic table. It wants to be an oxygen, okay? So it behaves chemically a lot like oxygen. Oxides are insoluble. Sulfides are almost always insoluble as well. This is group 1, that's why this one's soluble. So we're looking at lead sulfide as our solid. -2, +2, so that's good. We have 2 sodiums, 2 nitrates. Once again, we're going to need 2 sodium nitrates to make this balance out. Now, I can't encourage you enough to try balancing out some of these things. The lab 7 that we're going to do when we come back the Wednesday after spring break, that's what it's called, is going to deal with lots and lots of precipitation reactions. Make sure you can figure these out. Very important part of chemistry. As are redox reactions. Once again, in a redox reaction, we said the oxidation numbers change. Very, very important class of reactions. We're going to transfer an electron between a donor and acceptor. And that's going to result in the increase in the oxidation number or the decrease in the oxidation number, depending on which one you're looking at. What are the oxidation numbers? Once again, we've done this one. If it's an element, it's 0 by definition. Secondly, going back to chapter 3, if it's a metal, the oxidation number is the same as the charge. Magnesium bromide, magnesium is +2. Its oxidation number is +2. Lithium phosphide, the charge here is +1. Same as the oxidation number. If it's a metal, it's simple. just the charge. If it's a nonmetal, it's a little more complicated, but not much. We've already done the first rule. Elements are zero. Group 1 metals are always +1. That's these guys. Group 2 will be +2. Fluorine, way over here, most electronegative element, is always -1. So that's our always. Hydrogen, we know, has a split personality. It can be +1 or -1. If it's bonded with a metal, it'll be -1. Otherwise, it's +1. Oxygen is almost always -2. Halogens are -1, unless they're bonded to an oxygen. And finally, sulfur and selenium want to be just like oxygen. They're -2. Not really complicated rules. So let's look at how we apply these. This is a question, actually this question was an exam question once again. SO3, what's the oxidation number for each element? You look at it and you say it has an oxygen. I remember something about that. Oxygen is going to be -2. Now this whole compound must be neutral. So what's the oxidation number of the sulfur? It has to balance these 6 negatives. So it's going to be +6. That's not hard, is it? This is nitric acid, HNO3. Concentrated nitric acid can be bad stuff, can burn you very quickly, leave big brown stains all over your skin. It's used as an oxidizing propellant in kind of old-fashioned military rockets. In the Gulf Wars, every time you shot down a rocket, you released a cloud of nitric acid. That was a bad thing. All right, we look at this. We see two things. We have oxygens. They're going to be -2, right? We have a hydrogen that's bonded to an oxygen. We know that if hydrogen is bonded to a nonmetal, it will be a +1. So, our oxygen is -2, our hydrogen is +1. The nitrogen sitting here in the middle. We have 6 negatives, 1 positive. To make this neutral, nitrogen must be a +5. 6 positives, 6 negatives. Any questions? All right, here's a tutorial. This one's simple. Oxidation number of lead in lead nitrate. This also appears on Blackboard. We look at lead nitrate and we say, gee, lead's a metal. Right? Lead's a metal. Nitrate is -1. The oxidation number is simply going to be the charge. +2. Lead is +2. Hydrogen in pH 3. Well, Phosphorus is here, it's a nonmetal. So is hydrogen. The phosphorus bonded to the hydrogen, just like the hydrogen bonded to an oxygen was +1, this hydrogen will also be +1. That means the phosphorus must be -3. It's -1, the phosphorus is, I'm sorry, that should be a plus. Sorry. No, that should be, yeah, there it is. 1 and -3. Let me get that slide off of here. All right, like I said, redox reactions are very important in chemistry. When you look at a redox reaction, one of the games you play is to try to figure out who was oxidized and who was reduced. Now, very simple way to do this. You either remember one of these two things. Oxidation is loss of electrons. You can do it any other way you want. Loss of electrons is what I use. That means reduction is the gain of electrons. Simply remember those terms. So if we have this reaction, aluminum with iron 3 oxide, we will get iron and aluminum oxide. This is a single replacement where the metal replaces the metal. Who has been oxidized? Who has been reduced? Well, the aluminum is going to be 0, right? Oxygen is going to be -2. Iron is going to be +3. Over here, iron is the element. It's going to be 0. Aluminum is going to be +3. It's a metal ion. And oxygen, -2. So, who has excuse me, who has undergone loss of electrons? Aluminum has gone from 0 to +3. Does that mean it gained electrons or lost them? You had to lose electrons to gain a positive charge, don't you? This has been oxidized. Oops, this one. Iron went from +3 to 0. That means it gained 3 electrons. Aluminum has been oxidized. Iron has been reduced. Now, you know what? You're not going to see this on an exam or quiz or anything like that. But sometimes people decide to make things complicated for students. Okay? So there's a parallel nomenclature that goes on here. And that is oxidizing agent and reducing agent. The iron 3 oxide causes the oxidation. Therefore, because it causes it, it's called the oxidizing agent. The reducing agent is the thing that does the oxidizing. Again, I'm not going to use that nomenclature. I don't expect you to know it. But if you go to general chemistry, it's going to be everywhere. Well, this particular reaction is called the thermite reaction. This is again one that I used to do in front of 500 students in class, but they won't let me do it here. In this little flower pot up top, remember flower pots have a hole in the bottom, we have a mixture of aluminum and iron 3 oxide, just a mixture. This is sand in the bottom. What we're going to do is take a piece of burning magnesium, shove it in there, and run. As the reaction proceeds, see the stuff dripping out through the hole? That's molten aluminum. And the fun with this reaction is you're never quite sure when it's over. When it finally is over and it's safe enough to get close, that's a chunk of white hot iron. Isn't that kind of neat? Yeah. In the giant lecture hall, the students in the first 7 rows had to wear raincoats or whatever, because it really can just go everywhere. But yeah, big chunk of iron. Now, you may have noticed that this got really hot, right? Sadly, that has been used as a weapon of war. This is a thermite bomb. And yep, they used to fly over people's homes, drop these little suckers. They would burst into flames. This is a London neighborhood afterwards. Not a good thing. It's a shame because it's such a neat reaction. All right, look at these guys. Tell me, first of all, were they redox? Who is oxidized? Who is reduced? What type of reaction is this? 2 elements and a compound. It's a synthesis reaction, isn't it? We're starting with elements, so they're both 0. Fluorine's a halogen, it'll be -1, which means that the tantalum must be +5. So, tantalum has gone from 0 to +5. Does that mean it gained electrons or lost them? It means it had to lose 5 electrons. Oxidation is the loss. Therefore, this has been oxidized. Bromine gained an electron. It has been reduced. Single replacement, right? Element, compound, element, compound. The non-metal should replace the non-metal, right? Doesn't. Another exception, not a real important one. Silicone, aluminum oxide gives aluminum and silicon dioxide. Well, our silicon and aluminum will be 0. Our oxygens will be -2. This will be +3. The silicon, we have 2 negatives. This will be a +4. So, who has been oxidized? Silicon went from 0 to +4. Had to lose 4 electrons to do that, right? It has been oxidized. The aluminum has been reduced. Sodium sulfide, lead nitrate, lead sulfide, sodium nitrate. Lead sulfide will be insoluble, won't it? It's a double replacement reaction. Well, sulfur will be -2. The nitrate altogether is a -1. That means lead is +2. Lead is +2, sulfur -2, +1, -1. If you want to break down the nitrate, you can do it this way, +5 and -2. You go through all these numbers, they're the same. That's because this is a double replacement reaction that never involves redox. That's a sentence that's worth remembering for exam number 2. Double replacement reactions never involve redox. Whoops, sorry. Hydrogen, nickel to chloride. We're getting nickel and HCl. This is the time where hydrogen is acting like a nonmetal, isn't it? Hydrogen is 0, nickel 0. Nickel is +2, chloride -1. +1, -1. Hydrogen has gone from 0 to +1. That's a loss of 1 electron. And it has been oxidized. Any questions? Well, the third tutorial for this chapter. This is confusing as all get out, to be quite honest. VO +2. This is a polyatomic ion. Now, why do we only show this and not something bonded with it? Those are called spectator ions. This is a half reaction. So unless something is really involved, we ignore it. General chemistry, you will see half reactions everywhere. Again, designed to make it more difficult. Okay. So this is a polyatomic ion, VO +2 charge. We are going here to VO2 +1 charge. The question is vanadium oxidized or reduced? Well, let's take this guy apart. Our oxygen in VO is going to be -2, isn't it? So that means the charge on the vanadium must be +4. +4, -2, 2 positives left over. This guy, oxygen is still going to be -2. We have 4 negatives, but we have 1 plus left over. That means that this vanadium must be plus 5. 4 negatives, 5 positives, 1 plus left over. So the vanadium has gone from plus 4 to plus 5. Does that mean it gained an electron or lost one? Got more positives, it had to lose one. That's oxidation. Now, I tried not to put any of the really obscure ones like this on Blackboard, but there might be some that creep in there. Remember, it's from a big database, but I tried. Here's one that's really simple. Thorium plus 4 to thorium. Well, the oxidation number here is the same as the charge, plus 4. Thorium's an element. It's a 0. We've gone from plus 4 to 0. To do that, you had to gain 4 electrons. It's a reduction. Any question? All right, we are going to just look quickly at a concept here called the activity series of elements. Remember, I've said that these guys really get reactive, don't they? They react with water. We've seen potassium with water, very reactive as soon as it touches. This is defined by what's known as the activity series. Basically, the higher it is up on the series, the more reactive it is. Hydrogen fits in right here. If you take potassium, put it in water, potassium is above hydrogen, reaction goes like that. Sodium is above hydrogen, it reacts with H plus to give hydrogen gas and the ion. Not quite as fast as potassium, but still significant. There's a simple rule. First of all, you want to look to see how high your thing is on the table. The higher up it is, the more reactive it is. Secondly, we're going to have half reactions written like this. Sodium plus an ion to give something. If the element is more active than the ion, the reaction goes. It's a simple rule, really. If the element is above the ion, it goes. And the higher up it is, the faster it goes. So let's look at a couple examples. Silver and copper. The element is copper, the ion is silver. There's copper, there's silver. The element is above the ion, the reaction will occur. Copper is more active, it will replace silver in solution. We are going to actually do this in lab 7. This is a solution containing copper. I'm sorry. Containing, copper metal is what we added, and this is silver nitrate. Okay. After a few minutes, our copper metal starts to get really fuzzy. The longer it sits, this is 8 minutes, it gets really fuzzy. After a while, you kind of quit, 20 minutes, lots and lots of fuzz on the copper. What is the fuzz? It's silver metal. The copper has replaced the silver, and we're left with silver metal. The solution is blue now because copper nitrate is a blue solid. We're actually going to do this in lab 7. Our metal, our element is iron, our ion is copper. There's iron, there's copper. This reaction will proceed as written. We know that because we did the nail experiment, right? It's an activity series experiment. Here's a test question in disguise. One of these will work, one won't. Which one works? Element is aluminum, lead, is the ion. Aluminum's here, lead is here. The metal is above the ion. This will work, this one will not. Okay, let's finish up the chapter with a few old test questions. Aluminum and chlorine react to form a compound. Which of the following is true? This is the way it appeared. There was no equation given. The first thing you should have done is to write the equation. Aluminum plus chlorine, aluminum chloride. So, compound will be ionic. Of course it will. It's a metal. Oxidation number of aluminum in the reactants is 0. Of course it is. It's an element. Molecular formula is most likely AlCl3 plus 3 ion minus 1 ion. Yep, they're all correct. Which of the following are likely to be insoluble? Now, I put a disclaimer here, and I'll explain that to you. Actually, nothing is insoluble. There's an equilibrium constant called KSP, where SP is solubility. And it can be very, very large, which means it's barely soluble. But everything is, to some extent. But we're talking slightly soluble. All right, barium sulfate. We've seen this before. We know that barium, even though most sulfates are soluble, barium is a bad guy. Barium sulfate, classic, insoluble. Lead iodide, we saw the movie. Beautiful yellow compound, nicely insoluble. Copper nitrate, oh, it's a nitrate. Of course it's soluble. B and C, or A and B. What happens to fluorine in this? We have two elements making a compound, so it's a synthesis reaction, right? We know we are going to start off here at 0. The rule says that fluoride is always -1 because it's supposed to electronegative. All right. Change it from 0 to -4? No. changes from 0 to -1. Does not change? Well, that's wrong. Is -1 in the reactants? No, it's 0. It's an element. It's a none of the above. We go from 0 to -1. Fluorine has been reduced in this, hasn't it? It gained an electron. On the exam, I said you would get something like this, and you would give me oxidation numbers. This is one from a while ago. We see we have an oxygen. What do we say? Oxygen -2. That gives us 10 negatives. To make this neutral, each nitrogen must be +5. And let's wind up here with chlorous acid. HClO3. When we look at this, we say to ourselves, oxygen -2. Hydrogen is bonded to an oxygen, so it will be +1. We have this at -2, this guy at +1, 6 negatives, 1 positive. The fluorine must be +5. All right, I think this means we survived Chapter 5. Wednesday, no class. It's an extension of your spring break. Sit still, there's something important coming. And that's the tutorials. Balancing, assigning ox numbers, and redux. 15 points. Now, many of you learned exactly how important it was to do the tutorials in the first half of the course, right? And you're kind of kicking yourself. Some of you are. Some of you did them all. And that's great. Here's another incentive. Okay? We're going to have roughly 15 tutorials again for the second half of the course. You already have your total point for the first half of the course. After you take the second hour exam, check Blackboard. If your total is 350 or above, you will receive an A in the class instantly, and you will not be required to take the final exam. Let me say that again. 350, A, no final. Oh my goodness. If this is not an incentive to do all of these problems, none exists. Get busy and do every one you possibly can. Got it? Have a good break. See you in a week and a half.